In this video, we're going to look at some examples of interpreting proton NMR spectra. So this first one says the proton NMR of a ester is shown below. And then the first thing it asks us to do is to draw the displayed formula of the ester functional group. So that's just asking us if we remember that the ester functional group, it's acetyl bond O with an O that has R groups at either side, so carbon chains at either side. That's going to be important to help us identify things in our structure. And then we've been asked what can be deduced about the structure of the ester from the chemical shift. So the chemical shift at delta 2.20. So we're talking about this peak here. And we're going to look up 2.20 on our data sheet, which I've just put a little snippet of. And it's likely to be this here, because although there may be other things like ROH, alcohol, 0.5 to 5, we know that our structure is an ester, so it has acetyl bond O, so it's likely to be this 2.1 to 2.6. So that's what we can probably tell from the chemical shift. And what can we tell from the splitting? Okay, and our splitting here is that this peak is what we would call a singlet. So using the n+1 rule, if we're going to end up with one peak, then we mustn't have any neighbours, because no neighbours add 1 is one peak. So no adjacent protons. So we've got, what does the chemical shift tell us? Well, the chemical shift says it's a C double bond O next to a C. So it's this type of hydrogen. The splitting says no adjacent. So there's no hydrogens next door. So we know already from the picture there's no hydrogens on the left. But what we do know also now is that there's no hydrogens attached to the carbon on the right. So there is no carbon on the right. There is something else we can tell from this spectrum as well. If we look at the integration is a 3. So 3 H's of this type. Well, we've drawn 1 on already because the datasheet told us to. But if we were to put 3 on, we can then see why there can't be any next door neighbour hydrogens, because there is no next door. We've just saturated it with hydrogens and we're at the end. So this little jigsaw piece is part of our structure. And if we were to look now at our ester, it's probably this part is this, yeah, because we can't have the O, it's not in our little picture. So we're looking at our structure, we can see where we've got that from. I'm just going to delete that highlighting so we don't get confused. The next bit says the splitting pattern of the peaks. So it's sort of indicating that it wants us to look at 2 peaks together and think about their splitting pattern. So if we go up and look at 4.1, and that is a quartet. And then also at 1.2, and that is a triplet made of 3 peaks. So if we've got a triplet quartet, that is a common pattern that we have to watch out for. And a triplet quartet tells us that we've got an ethyl group. So we know that these peaks are due to an ethyl group. That looks like this. If we were to go back and maybe think about it a bit more, even though we're not asked to do that in this question, if we go back and we take each peak separately, so if I just get rid of that highlighting, the quartet is of integration value 2. So it's probably a CH2. And the quartet tells me it's next to, so the n+1 rule, if I end up at quartet 4 by doing something add 1, that something must be a 3. So we can see where the ethyl comes from, because it's 2, a CH2, next to 3, next to a CH3. And the location 4.1 probably indicates it's of this type. So this ethyl group is probably, we can sort of attach to the O of our ester from the information from its chemical shift. That isn't actually asked for in this question, that's why I've put it in brackets. And we can also double check our other peak, our triplet area of integration 3, area 3. So probably 3 hydrogens of this type, CH3, triplet. So if we end up with a peak of 3, something add 1, n plus 1 is 3, then the n is a 2. So next to 2 H's, so next to a CH2. So it's a CH3 next to a CH2. This is why the triplet quartet is an ethyl group, because it's a CH3 next to a CH2 and a CH2 next to a CH3. It's like doubly telling you the same information. So we know we've got an ethyl group on the O of our ester. We know we've got a methyl group on the C double bond O of our ester. These are our 2 jigsaw pieces. We just need to overlap them now, put them together and see that they're the same. So this top peak here that we've got, if I were to pick this up, so I can copy this and paste it down here, and maybe if you can imagine now, what we actually need to do is pick it up and flick it over. So we want to pick this piece up and we want to flip it over. So I'm going to have to do that by scribbling out, but you can imagine it in your head. I've picked it up and I've tipped it over, so it looks like this. Then I'm picking up my second piece, okay, this piece are just above, and I'm kind of overlapping it. It's going R C double bond O, because the C double bond O is the same C double bond O, like this. And then I've got to squish these 2 pieces together. So I've got to take this piece and I've got to bring it down and overlap it. And then we're going to rub out any kind of overlapping parts and make it look a lot neater. So I'm just going to take that out. We can see that this R here is the CH3. Then we've got the C double bond O, and this R is now becoming the O of our group, and we have come up with our structure. Our structure is ethyl from this part here, and then it's ethanoate from the other section. So if you need a little bit more to help you understand it, we've got this part here, excuse me, which is our singlet at delta 2.2. This is our quartet, because it's next to 3, at delta 4.1. And this is our triplet at delta 1.2.